Okay, so let us start with the lecture. So we are still discussing series. Now, last time I showed you how to determine whether an alternating series is convergent or not, and this was already our first example for a series where the terms are not necessarily positive. So if you look back, if you look at the tests we have introduced so far, so the first test was the integral test and then the comparison tests. For comparison tests we had two. One is a normal comparison test and the other one is limit comparison test. But all those tests just work for series where all the terms are assumed to be non-negative or positive. Okay, so if you look at, I think it's section 11.3 and 11.4, then you always see this requirement here, and this requirement was essential. Maybe I recall once more why this requirement makes life easier. The reason is because if you want to understand whether such a series is convergent or not, you have to look at the sequence of partial sums. Now, under this condition, this sequence is increasing. And for increasing sequences, it's much easier to figure out whether the sequence is convergent or not. You just have to prove the sequence is bounded, and that's it. But in general, if you do not have this requirement, Sn can behave much more complicated. And the general case is, as I have already emphasized, more complicated. But last time we looked at one situation where the an are not necessarily satisfying this condition, the alternating case, and the alternating case turned out to be very, very easy. Now, what we want to do next is we want to move to the general case. So we do not have this requirement anymore. We want to understand, okay, whether a given series, once more, whether a given series is convergent or not. And this is the most complicated case. Now, but also for this situation, we will see there are some tests which can be easily applied, and this will more or less finish our discussion of the convergence behavior of a series. Then we have enough tool for a given series to determine whether the series is convergent or not. And then we can turn to other questions. We first look at the following definition. Now, okay, we assume we have given a series which does not satisfy this requirement. Now the question is, okay, how to say something about the convergence behavior of this series. Now, the way we do it in mathematics very often, the principal idea in mathematics is, okay, if you want to understand a more general case, you try to relate it to special cases which you have already studied. Okay, so this is a general idea in mathematics. So if you have given a general series, okay, you might have the idea, okay, you do not. First, let's look at this series. So you replace this by this one. Okay, you look at this one. Okay, and maybe you can say, maybe if you, because this one we can study, because here the terms fulfill the requirement that they are positive, if unless an is equal to 0, but this is not important. Okay, so here normally we will be in the previous situation, so we are safe. Here we can say something, and then. Maybe there is a relation between those two cases. Okay, if there is a relation, we can use such an approach. That's why we make the following definition. So we call a given series, absolute convergence, if in fact this series is convergent. Okay, so this series is called convergent if the series of the absolute value is convergent. Okay, so let's look at some examples. So for instance, if you look at this series, the series, let's say n from 1 to infinity, minus 1 to the n minus 1 over n to the cube. Okay, so if this series is absolute convergent, because if you look at the absolute values of the terms you see you have 1 over n to the cube, and this series is convergent. So this series is absolute convergent. In fact, this series is also convergent, as we can easily figure out from the test we have seen last time, because it's the alternating series. So this series is both absolute convergent and convergent. Now, if we look at another example, this one. Okay, so this series, we know it's convergent because we know already. Last time I showed you how to find the value, ln of 2. How about absolute convergence? So if you look at the series where you replace the term by the absolute value, here you see 1 over n, so not absolute convergent. But convergent. Okay, so you see that if a series is convergent, this does not necessarily imply that the series is absolute convergent. Okay, but absolute convergent is more stronger property than convergent. Namely, whenever you know that the series is absolute convergent, the series will also be convergent. Okay, so absolute convergence implies convergence. And this is the real reason why we look at this notation. Because actually, this notation, if you see it, okay, so we give this series a property if this related series is convergent. If there is no connection, okay, if absolute convergence does not imply convergence, it would be useless to give such a definition. Okay, so the important result is that if you have absolute convergent, then you have convergent. Okay, but convergent is so absolute convergence is really a stronger property than convergent, which means that this direction is wrong. Okay, here's an example. Okay, but still, this is a convenient tool. So the proof here actually very nice. You look at this here. So an plus absolute value of an. This is larger or equal than 0, easily checked. Okay, and this is also smaller or equal than 2 times absolute value of an. Okay, so this chain of inequality is easily checked. Okay, it's easily true because an is smaller or equal than the absolute value of an, and larger or equal than minus the absolute value of an. So it's easily checked. Now you see, okay, we have absolute convergence. Okay, we want to prove convergence. So we see that okay, because of the assumption, we know that this here is convergent. So this, but this of course clearly implies that 2 times this series is also convergent. So you see by using this and the comparison test that this series is convergent. Okay, but once more, this series is convergent. So you can subtract this series from this one, which implies that the series over the an is convergent. Nice proof. You just use the comparison test, and you immediately get this result here, that absolute convergence implies convergence. So the normal strategy, if we have a series, this situation is more easy, but if we have a series where the terms an are not necessarily all positive, is, okay, we check for absolute convergence. If the series is absolute convergent, we can immediately follow that. This will immediately imply that the series is convergent. Okay, so for instance, an example. Okay, so note in particular that this number here is always even. Okay, so I have here minus 1 to the sum some positive integer, okay, and if you write out some of the terms here, you will see it's not alternating, okay. The pattern at which plus and minus changes is much more irregular than it's not just plus minus, okay. So this is different. This is not so you cannot use the alternating series test, okay. But still, you can easily conclude that this series is convergent. Namely, you just look at absolute convergence. Okay, so if you look at the absolute value okay, so this series here, okay, clearly this series is convergent. Okay, so and this will already imply that this series is convergent as well by this theorem here. Okay, so if you have given a general series, normally you check absolute convergence. But we have already seen there are examples of series which are convergent but not absolute convergent. These are really the hard cases. Okay, those series are really the bad guys. Checking that they are convergent or not normally is not so easy. And such a series which is convergent but fails to be absolute convergent it's called conditionally convergent. Okay, so this is the following definition. A series is called conditionally convergent if it is convergent but not absolute convergent. Okay, and we saw already one example for such a series. So this series n from 1 to infinity minus 1 to the n minus 1 over n. Because of the alternating series test, it's easily seen to be convergent. But if you look at the absolute values, it's the harmonic series, not convergent. So this is an example for a conditionally convergent series. And we will see, roughly speaking, absolute convergent. If you have an absolute convergent series, okay, then everything which is true for a sum holds for an absolute convergent series as well. We will see some properties afterwards. But if you have a conditionally convergent series, the situation can be much more complicated. Okay, so a conditionally convergent series has some properties. So for instance, if you have a sum, okay, sum of n numbers, you know you can change the order, okay, and the sum always will be the same. Okay, it's for finite sums. Now, for a series, okay, if you want to change the order of terms, okay, if you just change a finite number of terms, the order of a finite number of terms, of course, the series, this will not affect the convergence behavior, and the sum will be the same. Okay, but the question is, more complicated question is, if you change an infinite number of terms, okay, does this have an effect on the convergence behavior? And we will see for absolute convergent series, no, but for conditionally, yes. Okay, so conditionally, roughly speaking, absolute convergent series, you can treat them like sums, like finite sums. But conditionally convergent series, you have to be careful. Okay, I will stress this in a little bit more details a little bit later, but because first I want to introduce now two more tests for testing convergence of series, the so-called ratio test and the root test, and these are maybe the most strongest of the tests we have learned so far, also most convenient of the tests. Now, in order to motivate the main idea, or in order to explain the main idea behind the ratio test, I will go back to the case of a series which has where all the terms are positive. So where I do not have this problem here with absolute convergence. But the test then will be for general, will also work for general series. Now, I showed you already before or previously I showed you already previously the following example. So for instance, this one, e to the over n factorial. Okay, so we know already that this series is convergent. Okay, just to remind you, okay, the way we proved this, okay, we established that the following that this inequality holds for all n larger or equal than 7. Okay, and this then means that e to the n over n factorial will be smaller or equal than e over 3 to the n. But this is smaller than 1, and because this is a geometric series which is convergent, this will be convergent as well. So this was our idea we used last time. Okay. Now this is not very complicated. Okay, but you see that kind of step which makes this approach not so easy in some cases is okay. You have to find such inequalities. Okay. Now if I give you other examples, you have to find other inequalities. This is maybe so the. Sometimes applying the comparison test is easy because you can easily see some inequalities. But sometimes it would require more work. Like here, this is not really complicated, but at least you have to come up with this idea here, with this inequality in order to find it. So the ratio test will avoid this by using another idea for the same series. Now, what would be another idea more clever than this one? This is not really stupid, okay, but it just applies for this series. Okay, if you have another one, it doesn't apply more generally. Now, a more clever idea is the following. You observe the following. If you look at the ratio of two terms, then you see, okay, you plug in, so you have e to the n plus 1 over n plus 1 factorial, okay, and then the an is n factorial over e to the n. Okay, so you see that this will give e to the n plus 1, and you observe that as n tends to infinity, the ratio tends to 0. Okay. Now, why is this a crucial observation? Why is this a good observation? Because you know that, okay, from the limit definition, okay, this means that, okay, there exists an index n, okay, such that this ratio here, I do not have to write absolute values because the terms are all positive, okay, or let's write at least once there. So, but I can avoid it, okay, will be smaller or equal than any epsilon, okay. As n is getting large. So for instance, I can choose 1. Okay, maybe 1 is not the best choice. Let's choose 1/2. Okay, for all n larger or equal than n. Okay, so this means here that an plus 1 will be smaller or equal than 1/2. If I use this index n here, so this means that if I plug in for this small n, large n, okay, this will hold. So capital N plus 1 is smaller or equal than a capital N. Okay. Okay, but I can do the same for a capital N plus 2, which will be smaller or equal than let's do it slowly here. So it's smaller or equal than 1/2 an plus 1. But then I plug in this here. So this will be smaller or equal than 1/2 square an. Okay. So you see from this, you easily get that an plus k, okay, will be smaller or equal than 1/2 to the k, okay, an, for all k larger or equal than 1. This is even true for all k larger or equal than 0, trivially. Okay. Now, why is this a good observation? Because you see here something emerges, shows up, which is related to the geometric series. Okay, so this means here that if I sum up, if I consider the sum or the series where I where I throw away the first n minus 1 terms, so this one, then this will be smaller equal than this series 1/2 to the k an. Okay, but this one is convergent. Okay, so this one will be convergent as well. Okay, so I can follow from this that actually I shouldn't write this like this because I do not know whether this is convergent. So you see that this inequality is enough, and the observation that this series is convergent. Okay, so you see that from this you can follow, using the comparison test, you can follow that this series is convergent. Okay, and this will then imply, if you add again the n minus 1 terms we have removed, this of course implies that the original series is convergent. Now, what is my main point? The main point here is, you see I have removed the original example. So this will work whenever an plus 1 over an tends to 0 as n tends to infinity. You can use the same reason. Okay. So actually, if you have a series and you have that an plus 1 over an tends to 0 as n tends to infinity, you always will have that the series is convergent because of this reason here. And actually, it's not really necessary that this ratio here tends to 0 as n tends to infinity. It just has to tend to something which is smaller than 1. Okay? Why smaller than 1? Because here that I chose something which is smaller than 1 is essential. Okay? Because otherwise, if I choose here a c, okay, I get here c to the k. Okay? No matter what the c is, but the c must be smaller than 1 in order to have that this series here is convergent. So whenever the ratio here tends to something which is tends to a limit which is smaller than 1, we can use this here in order to derive that the series is convergent. Okay, and so actually this I looked at this ratio, okay, because here in this case an is always positive, okay. But if this is not the case, then I just look here at absolute values. Then I have everywhere absolute values, and I test absolute convergence. Okay, but the same. Okay, so in general, if you have that the absolute value of an plus 1 over an tends to a limit which is smaller than 1 as n tends to infinity, then the series over an will be absolute convergent, hence convergent. Okay, and this is an interesting observation. You see, this is because this is normally quite easy to check. We just saw it for this series. Kind of easier than to come up with suitable bounds in order to use the comparison test. Okay, so essentially this idea gives the so-called ratio test. Okay, so any questions to this? You see, what you should understand for the ratio test is here the main idea. The main idea is this here. So the ratio test is nothing else but comparison test where you compare with the geometric series. That's it. But the comparison test for the ratio, so the ratio test rewrites the comparison test such that it's more easy to apply it. Okay, so we have given a series. Now you have three cases. The first case is limit n tends to infinity, absolute value of an plus 1 over an, okay, smaller than 1. Then, okay, you just saw the how to argue. Then you can show using the same in this general situation, using the chain, the same chain of reasoning. You can show that the series is convergent, not only convergent, even absolute convergent. Okay, so this is the first case. Now the second case. If the limit n tends to infinity, absolute value of an plus 1 over an is larger than 1. Okay. So in this case, the series is divergent. Actually, this is also easy to see, okay, that the series in this case must be divergent. Okay, why? You see, if you have this condition here, okay, then this condition here means, by the definition of the limit, okay, this means that you will have that this ratio is larger than 1, okay, for all n which are large enough. Okay, this is the definition of the limit. Means, okay, this ratio will be larger than 1 for all n which are large enough. Okay, but you see that this condition means, okay, your sequence an is moving away from 0. Okay, because this in particular means that all the an for n is larger or equal than n are larger than the absolute value of a, and then you replace small n by capital N. Okay, so you cannot move to 0. Okay, so this clearly means that the limit an n tends to infinity is not equal to 0. Okay, but then we know that, okay, this means divergence. Okay, so this case is also this is also easy. Okay, now you see. So any questions to this? Now you see, okay, there is only one situation left, namely the limit is equal to 1. And in this situation, no decision. Okay, so this test is useless in this situation. So this is easy to see because if you look at this series 1 over n to the p, okay, our p series, you see that okay, if you look at the ratio is 1 over n plus 1 to the p over 1 over n to the p. Okay, and here in this case equal to 1, no matter what the p is. Okay, but we know that if p is larger than 1, convergent, p smaller or equal than 1, divergent. Okay, so it's not possible to have a conclusion in this case here. Okay, actually I said here this is the last case which is left. Okay, but it's not really true. Okay, these are not the only three cases. Okay, because another situation which is not discussed by the ratio test is the case where this limit does not exist. Okay, so all the three cases are just applicable if the limit exists. Okay, smaller than 1, larger than 1, or equal to 1. But it could also happen that this limit does not exist. Okay, and then the situation is also more complicated. Okay, so this is the ratio test. If we compare now the ratio test to the previous tests, okay, comparison test, you see that the first part of the ratio test, okay, which checks whether which tells you the series is convergent, is actually just the comparison test in disguise. Okay, namely, I compare here with the geometric series. Okay, that's what I'm doing. Okay, the only thing the reason why I reformulate the comparison test like this is because it's more convenient. Okay, but normally, I shouldn't say normally. If you can apply the ratio test and get convergence, clearly you can apply the comparison test as well. Okay, so this is kind of like stronger. This is a better condition to check for the comparison test, and this is just a test for divergency. Okay, and here in this case, I do not have a conclusion anyway. But normally, this is one of the best tests which we will learn in this lecture and which we will clarify for many series. The convergency behavior. Unless you are here at the boundary, then you have to use some different tool. Okay, so let's maybe look at some examples. So you see one. Another example is this one. 1 over n to the n. So maybe let's check how to use the ratio test for this example. Okay, so we have to look at the ratio. So the limit n tends to infinity. Then we have so we have n to the n over n plus 1 over n plus 1. Okay, so what can we say about this limit? Now we have the limit n tends to infinity. Okay, so we take out the 1 over n plus 1. So what is left is n plus 1 to the n. Okay, and this we write as 1 over, and then 1 plus 1 over n to the n. Okay, now if you write it like this, the limit is easy to figure out, because you know that this limit here is e. Okay, so you have here 1 over e, but this is 0, so everything is 0. Okay, so and you can immediately, in the first case, you can immediately conclude this series is convergent. But actually, who sees a much easier way to do this? Actually, for this case, this is not the best method, because n to the n okay, so you see that you can compare. So you see that 1 over n to the n smaller equal than 1/2 to the n. Okay, this is convergent, this is convergent. Okay, would be easier. So you see that in this case, maybe it's not the easiest. The ratio test maybe not the easiest test, but it's more systematic because you can apply it in a systematic manner. Okay, so you see also the difference between the ratio test and the comparison test. The ratio test and the comparison test. The ratio test is something which Maple can do as well. You can check with Maple whether this is whether this limit is smaller than 1. Okay, but Maple, unless you tell Maple, will not be able to come up with this idea. Okay, so you can use a much more systematic approach now, checking whether series are convergent or not. Let's look at some other examples. Here's a square. What would you guess? If you look at this series, what would you guess? Convergent or divergent? Maybe let's just check it with the ratio test. Okay, so you have 2n plus 2 factorial over n plus 1 square over, and then you have 2n factorial over n square. So this is equal to the limit n tends to infinity. Okay, so you have n over n plus 1 square. So this will be 1. And you have 2n plus 2 factorial over 2n factorial. Okay, so you see that you have the limit n tends to infinity, n over n plus 1 square. And from this you see that, okay, so this is 2n plus 2 times 2n plus 1. Okay, so infinity. Okay. Because this tends to infinity and this tends to 1, so everything will go to infinity. Okay, so this means divergent. But this is not the only way to show this, okay? Because what you would expect divergency anyway, okay? Because this here will grow much faster than this one. Okay, so actually, if you check whether this limit here tends to 0, no, it doesn't tend to 0, it tends to infinity. So also the test of divergency would apply. Okay, but you see that the ratio test is like convenient, okay, because you can apply it very systematically. this one, 2 times, 4 times, and so on, 6 times 2n over n factorial. Okay, so it's essentially a question of which one is tending faster to infinity, this one or this one. Okay, so you can also you could also first check whether the limit of the term tends to 0 or not. Okay, but we apply the ratio test. I just want to tell you this kind of thing. Okay, in mathematics we use here the n factorial means one step, and if we have something like this here, in mathematics normally we write this here. Okay, two factorials. So which means you go 2 steps. Okay, so if we look at the ratio, okay, we have here 2 times, 4 times, 6 times, and so on times, okay, 2n. We have to replace n by n plus 1, so we have here this one over n plus 1 factorial over, and we have the same here, so 2 times, 4 times, 6 times 2n over n factorial. So this will be the limit n tends to infinity, 1 over n plus 1. Okay, and you see that also here most of the terms cancel out. The only one which is left is this one. Okay, so the limit is equal to 2. 2 is larger than 1, so divergent. Okay, so you see it's very easy to apply the ratio test. Okay, of course in this situation you could do it different. Okay, you could also try to find bounds in case of, but this is divergent, so the first thing would be to check whether this really tends to 0 as n tends to infinity. But maybe you need an idea for this, but it's not very complicated to check this either. Okay, so you see actually that this term here, because you take out from every term you take out a 2, okay, then you get 2 to the n times n factorial. So what you have here actually 2 to the n, and 2 to the n tends to infinity as n tends to infinity. So this would be much easier than applying the ratio test. So you see you always have many different choices. Sometimes it's good to simplify before you use the tests, but you see that the ratio test is a convenient tool. In particular, you can also handle something like this here. Okay, the question here is a little bit different. For which x is this series convergent? Okay. Now, here you could also use my, because I showed you if x is equal to e, okay, how to do it. So I just tried to find a suitable inequality for n. I could do the same, okay, for general x, but okay, it's a little bit more complicated to write it down. But it's very easy to check for which x is this series convergent by using the ratio test. So you have now you really have to use the absolute value because x could be negative as well. So you have the absolute value of x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. Okay, so you see that this is the limit n tends to infinity. You see absolute value of x, and then you have 1 over n plus 1. Okay, so no matter what the x here is, this will always be 0. Okay, so you see this is convergent. Okay, we will later on next week we will prove actually equal to e to the x. Okay, so next week we will be able to sum something like this. Okay, so this is another example. Now, actually, all the examples I showed you, this is an exception. Okay, is the terms for the other examples, all the terms were always positive. Okay, so but this is an exception here. So here we have really to check here. We even know more than convergence here. We know absolute convergence. Okay, so this series is absolute convergent for all x. Okay, now for this series, which I showed you before, so this one, okay, there is actually an easier way to do it. We saw using the ratio test is not very complicated, okay, but it is much easier to use another test, which is the so-called root test. And the root test and the ratio test are very similar. So the root test is also for a series, and you again have three cases. The first case is the only thing you look at something different, okay? Not at the ratio. You look at the nth root of the absolute value of an. Okay, and again, if this is smaller than 1, then you have absolute convergence. Okay, if this is larger than 1, you have divergence. And if this is equal to 1, you have nothing. I mean, you have no decision. Okay, so this is similar. Similar is the ratio test, but you test something different. Actually, I'm not sure whether the proof is in our textbook. Maybe it's an exercise, because the proof is not very complicated. It's the idea is very similar to the idea you have seen for the ratio test. So again, here again, what is behind the first point is comparison with the geometric series, and using the concept that absolute convergence implies convergence. What is behind here is this is easy. Okay, this is like because if this limit is larger than 1, you know that the nth root of absolute value of a of n will stay larger than 1 from some index on. So this means that the absolute value of a of n will be larger than 1 from some index on. So it's no way that an goes to 0. Okay, so this case is easily explained. And here you have you can again look at the example 1 over n to the b, and you will easily see that there is no decision in this case because this limit will be 1 if an is 1 over n to the b. Now, the reason why we look at this test is like the same. It's pretty similar to the ratio test. It's just more convenient in some cases. Like for this example, it's obviously more convenient because you immediately see infinity of the nth root of 1 over n to the n. Because this here is easily computed, 1 over n is equal to 0. So you can immediately follow that this series is convergent. So the only difference to the ratio test, using the ratio test, is that the limit here is easier to compute. Okay. So this test always applies if you have terms which include the power of n. Okay, then you normally will choose this test. So for instance, if you have something like this here. So for instance, if you have something like this here, you will the test you use naturally, the root test, okay, because here you see that the limit as n tends to infinity of the nth root of 2n plus 1 over 3n plus 1 to the n is equal to 2 over 3, smaller than 1. So you're in the first case, absolute convergence. Okay, so this is kind of the last test we will learn in this lecture, ratio and root test. And this is also kind of the ratio test is the one normally which will, for most of the examples, which will be which you can apply, unless you are in the third case where the limit is equal to 1, then you have to choose another test. But the ratio test will apply in many cases. The next thing we have to do is, so we will move on because we have now discussed series for a long time, and you might start to question why should we do this? Why are we interested in series? So I should start to give some motivation as for why series are so important in applications. Now, before we do this, I just want to say a few words about rearrangements of series. So I discussed this problem already at the beginning of the lecture today. So a fundamental question is, of course, whenever you look at a series, you tend to believe that you can just treat it like a finite sum. Okay, so you have a series. Okay, the question is, okay, all the rules you know from finite sums, okay, are they true for a convergent series as well? Now, one such question would be, okay, if you rearrange the order, okay, of the terms is the rearranged series again, if the original series is convergent, is the rearranged series again convergent? And if yes, is the limit, is the sum the same? So for instance, you do something like, this is A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7, and so on. So for instance, you do something like here. You switch always these two. Okay, so you switch these two. So you first have A1 plus A3. So the question is, okay, A1 plus A3, and then plus A2. And then you go on A5 plus A7, and then A4 plus, and you go on like this. So here you switch. You not only switch a finite number of terms, okay? If you have a convergent series and you change the order of a finite number of terms, nothing will change, okay? The series will still be convergent, okay? Because a finite number of terms do not affect the convergence behavior. And sum will be the same. But the question is, okay, if you change an infinite number of terms, okay, is it possible that the resulting series, for instance, becomes divergent? Okay. Now, if the original series is absolute convergent, the answer is no. So if you have an absolute convergent series, no matter how you rearrange the series, okay, infinite number of terms, the rearranged series will be absolute convergent as well, and has the same sum. Okay, nothing will happen for an absolute convergent series. Okay, so you can rearrange terms. Now, how about a conditionally convergent series? Okay, so let's look at our toy example, this one. This is conditionally convergent. Okay, so we have 1 minus 1/2 plus 1/3 minus 1/4 plus 1. I just write some more terms. Okay, so this we showed last time. This is equal to ln of 2. Now let's multiply everything with 1/2. Okay, so we have here 1/2. So maybe I write it also a little bit different. So I multiply everything with 1/2. So I write here 0 plus, then the first term 1/2 plus. I always add the 0 in between. Okay, so 0 plus 1/2 plus 0. Now the next one is minus 1/4 plus 0. Then the next one is this one, so plus 1/6 plus 0. Then minus 1/8 plus minus. Okay, so this will be 1/2 ln 2. Okay, I just multiply both sides with 1/2. If it is convergent, okay, I can do this. I can add those zeros. Okay, it doesn't matter. Okay, still the series will be convergent and equal to 1/2. Okay, now I add those two. Okay, so both are convergent, so I can add them. Okay, so you see on the right-hand side you get 3/2 ln 2. Okay, and what do I get at the left-hand side? So you see I have 1. This one cancels, plus 0, plus this one is 1/3, plus, and this one is minus 1/2, plus 1/5. This one cancels, plus 0, plus 1/7, and this one becomes minus 1/4. You will observe that now you remove all the zeros. Okay, so if you remove all the zeros, what do you get? 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6 plus minus. And you see, this is the original series rearranged. Okay, namely, I start with the first two odd terms, then the first even term, then the next two odd terms, then the next even term, and so on. Okay, but the result is different. Okay, from here. And the main thing is, if you start out with a series which is absolute convergent, this can never happen. Okay, but if the series is conditionally convergent, this can happen if you rearrange it. Okay, then the rearranged series might be convergent as well, but the sum is not the same. Okay. So conditionally convergent series behave different from absolute convergent series. Now, actually, for conditionally convergent series, the situation is much more crazy. Okay. Namely, Riemann proved, okay, that whenever you give me some value, so if, for instance, you give me 1,000, I can tell you how to rearrange this series such that it's convergent and the sum is 1,000. Okay. So for any number you give me, there exists a rearrangement of this series such that the rearranged series converge to this number, also including plus infinity and minus infinity. Okay. So I can also make this series. I can rearrange it such that it becomes divergent. Okay. So this is a famous result of Riemann, which is not very complicated to prove. And it's so easy to prove that there are exercises in our textbook which let you prove, which tell you how to prove, which give you some instruction how to prove this result. So it's not so complicated. So it's possible to prove with your knowledge. So if you're interested in proving this theorem of Riemann on your own, then check out our textbook. I think it's, which section are we? 11.6 or what is it? 11.6, it should be 11.6 in our textbook. The last two exercises, okay, tell you how to rearrange, for instance, this series or any conditionally convergent series such that you achieve convergence to any number you wish. Okay. Not only this one. Okay. Also, for instance, 10 to the 10. Okay, it's possible. Okay. Any questions? So this is just to let you know that also a series has many properties which are the same as the properties which you know from finite sums. Okay. Not all the properties hold. Okay. And roughly speaking, for an absolute convergent series, okay, an absolute convergent series, you can do whatever you want. Okay. And it's if the corresponding law holds for the for a finite sum, okay, it will hold for absolute convergent series as well. You can rearrange it. You will always get the same value, and so on. Okay. But for a conditionally convergent series, these are really the bad guys, the complicated guys. Okay. They behave different. Okay. And we will also in the next sections, the main situation we will mainly discuss is absolute convergence, not conditionally convergence. Conditionally convergence makes life complicated, very complicated sometimes. Okay, so if you are interested in understanding such phenomena, you can just take our textbook 11.6. The last two examples are pretty nice, and you can try it on your own. Okay, now the next thing we want to talk about is a special class of series, namely power series. Okay, so what is a power series? A power series is an object which looks like this here. Okay, so this is called a power series. Okay, so the reason why we look at such series is should be quite clear if you just look at the form. So maybe let's first write out some terms. I should mention that for Syrah, okay. For Syrah, I normally use the convention here. So always this one. Okay. So if you plug in here Syrah, okay, for x, okay, and compute this, then what you get is a Syrah, okay. So I always use this convention here. It's the usual convention in mathematics, okay. So if you multiply something 0 times, it will be 1. Okay, this is the usual convention in mathematics. So such an object is called a power series, and you from this form you easily see why we are interested in such objects, because this is the natural extension of a polynomial. Okay, it's a natural extension of a polynomial function. A polynomial function is something which is easy, also very easy for the computer, because the computer knows normally how to multiply, how to add, and so on. So this will be a natural extension of the class of polynomials. Okay. And the question normally is, okay, for which x? Our first question is always, okay, this is a series for us, so for which x is the series convergent? Okay, so for those x, we can define here a function f of x, which is called then this is the sum of the series. Okay. Okay, and this and the domain of this function, okay, is given by the set of all x such that this series is convergent. Okay, so the first thing which we wanna do is we wanna understand the domain, the possible domain of such a series, the possible domain of such a function. Now we even do it a little bit more general. We also allow a shift. So we also look at such a power series. So also this is called a power series. In x minus a, or centered at x is equal to a, centered at a. So this is normally the language which we use. This is called a power series in x minus a, or centered at a. So we normally look at a slightly more general class of functions which involves this shift here. And you see that if you ask, okay, for such a general power series, okay, what are the possible x such that the series is convergent? Okay, there is always one x, namely x is equal to a. Okay, for this trivial. Okay, so such a power series is the domain of its sum. Okay, is never empty because x is equal to a is always a point where this power series is convergent. But the question is, okay, are there others? If yes, okay, how does the set look like? Does it have an easy structure, or can it be very complicated? Okay, so maybe let's look at some examples. N to the n, x to the n. Okay, so how about this power series? So for which x does it converge? Now we have now two tests, okay, which are suitable in order to check this: the root test and the ratio test. So in this, because of the structure of this example, we will naturally use the ratio test, the root test. Okay, so you see that this is the limit. N tends to infinity, absolute value of x times n. And you see, okay, you have here two cases. Namely, if x is equal to 0, then this will be 0. And if x is not equal to 0, this will be infinity. Okay, so which tells you that this series is convergent only at x is equal to 0. Okay, so convergent only for x is equal to 0. Now, another example would be this one. This one. Okay, here we use the ratio test. Okay, so we have the absolute value of x minus 1 to the n plus 1 over n plus 1 over, and then the absolute value of x minus 1 to the n over n. Okay, so we see that this is the limit. N tends to infinity, absolute value of x minus 1. This is actually a constant, so we can take it in front of the limit. And then we have n over n plus 1. Okay, so this will be absolute value of x minus 1. Okay, so we see that convergent for now from the ratio test we get convergence if this is smaller than 1. Okay, so and we get divergence if this is larger than 1. Okay, so this is if we look at the numbers here. So we see that we have convergence here already. Okay, we have divergence here. And there are two cases which are left to check, namely because from the ratio test we do nothing about those 2 points here, 0 and 2. If we plug in x is equal to 2, okay, we get 1 over n. So here for 2 also divergent. And if we plug in x is equal to 0, we get minus 1 to the n over n. And because of the alternating series test, here convergent. Okay, so you see that this is this series, this power series is convergent for x in the half open interval from 0 to 2. Okay, and here is a third example. So maybe it's convergent only for x is equal to 0. For this one, okay, so this series we already checked before. So this is also a power series, and we already saw before using the ratio test that this series is convergent for all x. Okay, so these are 3 examples. So maybe I erase this and write here convergent for x okay, so these are 3 cases. So this is the first case. Now, our next theorem tells us essentially these are all cases. Okay, so if you have a power series, then there are essentially 3 cases. The power series is convergent only at x is equal to a, so at the point at which the power series is centered, or the power series is convergent for all x, or if both is not the case, then the power series is convergent on such an interval, okay, which is either open or closed or half open. Okay, nothing else can happen. It cannot happen that a power series, for instance, is convergent on this interval joined with, for instance, this interval. This cannot happen. Okay, so the 3 cases you see here are already a classification of the convergence behavior of a power series. Tell you already what is possible. We have given a power series, so series n from 0 to infinity, a n x minus a to the n. Okay. Then one of the following situations occurs. First, convergent only. So this situation, convergent only for x is equal to a. Second, convergent for all x in R. So this would be this situation. Or third, there exists the R larger than 0 such that convergent for all x with the absolute value of x minus a is smaller than R and divergent for all x with the absolute value of x minus r is larger than r. And the behavior at the boundary of this, because this gives you an interval of convergence, namely from a minus r to a plus r, this interval. And at the boundary, you have to check. The boundary, so the two boundary points, like here 0 and 2, you have to check individually. It could be that the whole interval is the interval. It could be that the power series converges at the whole interval, or at the half-open interval, or at the open interval. And this R is called the radius of convergence. Radius of convergence. Normally, we use the ratio test in order to compute the radius of convergence. Of course, you can also use the root test in some cases, but normally we use the ratio test. And then this interval, so it's either like this, or it is half open, or like this here, or it's closed. This depends on the situation, because you have to check the boundary points. It's called interval of convergence. Okay, so this is radius of convergence, and here interval of convergence. The radius of convergence here coming from the 0.3. Normally, in those two situations, we say that here the radius of convergence is 0, and here the radius of convergence is infinity. So we include this in the notation of radius of convergence. Maybe you might wonder why this is called radius of convergence. Why radius? The reason is not visible here, but you can do the same for complex numbers. Then you are in the complex plane, and then you get in the complex plane you have the same result. But the meaning of this in the complex plane becomes this is all the points x which are inside the circle centered at A with radius r. So then it really is a radius. You will later on you will have a class I think next year which is called complex analysis, where you will learn similar stuff, but just for complex numbers, where can be big differences to the things in the phenomena which we learn today, which we learn in this semester. But the theory of power series is kind of becoming more easy if you look at it from a complex point of view. But this is something you will learn later on. So we will see next week that there are some things which are more tedious, more complicated for the real number case, which then become easy if you next semester if you go to the complex plane. Okay, so maybe let's look at some last example. If you're interested in the proof of this result, okay. Actually, the proof is not complicated, but not completely easy. So you need some fact which is explained in the textbook. So if you are interested in the proof of this result, feel free to look at the appendix of our textbook and read it on your own. It's not very complicated, but the proof is quite important, because the proof tells you, okay, gives you a feeling why such a result is true. It's more or less, the proof is just comparison test, more or less, but you need some facts from which comes from the definition of the real numbers, which we have never done. So you have, but it's explained carefully in our textbook, so you can read it on your own if you're interested in such theoretical things. So just give me a few more minutes to look at one example. This power series. Okay, so the natural question for such a power series is always the same question: for which x is the power series convergent? Okay, so we use the ratio test. So we have to look at the ratio n plus 1. Absolute value of x minus 4 to the n plus 1 over n plus 1 to the cube plus 1 over, and then n absolute value of x minus 4 to the n over n to the cube plus 1. Okay, so this is not too complicated. So this is the limit. N tends to infinity. Now n to the cube plus 1 over m plus 1 to the cube plus 1. Then you have m plus 1 over n. And you have an absolute value of x minus 4. So you see that the limit here is 1. The limit here is 1. So what you get is absolute value of x minus 4. From the ratio test, you will get, okay, convergent. So the radius of convergence here is equal to 1, centered at 4. Okay, so you see that the interval of convergence is from 3 to 5. Okay, but we do not know whether 3 is included or not, so we have to check the two boundary cases separately. Okay, so we check x is equal to 3. Now, for this situation, we have the series n from 0 to infinity, n over n to the cube plus 1 minus 1 to the n. Now, what can we say about this series? Okay, so here we will use, because alternating, so we will use the alternating series test. This sequence easily seen, of course, as n tends to infinity, will tend to 0, and is easily seen to be decreasing at least from some point on. Okay, so by the alternating series test, for the homework, you have to write more than this. Okay, you have to explain why the alternating series test applies. But I'm more lazy, so I have done this already very, very often. So believe me, it applies here. Okay, so because of the alternating series test, convergent. Now for x is equal to 4, which is the other, x is equal to 5, which is the other critical case. So here you have the sum n, or the series n from 0 to infinity, n over n to the cube plus 1. And what can you say about this series? Convergent because of what? So you don't have to look at this one. Then you get 1 over n squared. So 1 over n squared is the sequence with which you compare using the limit comparison test. But the series over 1 over n squared is convergent. So using the limit comparison test, you get convergence. So the interval of convergence is the closed interval from 3 to 5. Okay, so this is one example. So you see, then for the homework examples, okay, please be a little bit more careful. So not just names and so on. So tell me why, okay, why the limit comparison test here applies and so on. You see, these are normally nice examples where you can. Where I can check whether you know how to apply those tests, because normally we need a couple of different tests in order to figure out whether a series, such a series, or where such a power series is convergent. Like another good example is this one, where p is larger than 0, okay, depending on the parameter. Okay. Now again, I'm interested in the domain of convergence. So I first look at the ratio test. So I have the absolute value of x to the n plus 1 over n plus 1 to the b over the absolute value of x to the n over n to the b. So you see this is the limit as n tends to infinity, n over n plus 1 to the p, absolute value of x. And this limit here is always 1, so you get this here. Okay, so the radius of convergence is again 1. Okay, and the interval of convergence you see, the interval of convergence is from -1 to 1, okay? But I have to check the two boundary cases. So if x is equal to -1, this series will always be convergent. If x is equal to 1, the series will be convergent only if p is larger than 1. So what I get here, okay, is I have to look at two cases. One case, this one, and the other case, this one. Okay, so in this situation, I get the half-open interval from -1 to 1, whereas in this situation, I get the closed interval from -1 to 1. Okay, because once more, from the radius of convergence, you already know the interval of convergence is from -1 to 1. For the left endpoint, x is equal to -1. Because of the ratio test, okay, this series is always convergent. Okay, so here this point is always included. And for the right endpoint, x is equal to 1, you have 1 over n to the p, our p series, which is convergent if and only if p is larger than 1. Okay, so this point is only included if p is larger than 1. Okay, you see these are good examples where I can check whether you understand how to use all these kind of tests, because I use the limit test here, I use the alternating test here, and for here, actually 1 over n to the p, okay, for this I had to use, if you remember it, the integral test to figure out whether this series is convergent or not. So here you see the ratio test, the alternating series test, and the integral test are all included into one example. So these are normally good examples where I can check whether you understand all those tests. Okay, so any questions? If not, then that's it. We will meet on Monday.